Okay, question number 3 in our series here from our third AP Chem quiz. Again, I'm working from the perspective of the hydrocyanic acid. So this is question number 3. These questions all looked pretty similar to each other, but they were all different. All right, reading carefully is a critical skill. So here's the deal. In part A, determine the pH of a solution that is 0.200 molar in the acid, that is HCN in my case, and is 0.200 molar in the conjugate base, that's CN minus. So notice what's new here. I have both the acid and the conjugate base. Both are present at the same concentrations. I hope bells and whistles are going off inside your increasingly sophisticated AP chemistry head, and you're saying to yourself, ding, 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 I've got an acid, I've got the conjugate base, they're present in the same concentrations. I know that's the best buffer. pH equals pKa plus the log of the concentration of the cyanide divided by the concentration of the HCN. Plug that in. 9.21 is the pKa for HCN, plus the log of 0.200 molar for the base, 0.200 molar for the acid. Concentrations are the same. I have the best possible buffer. My pH is equal to 9.21. And again, best buffer because the concentrations are the same. Okay? I've got just as much capacity to handle adding strong base as I have for adding strong acid in my solution. All right? Good. Now, we come along, and now we're going to mess up solution A. We're going to take solution A, we're going to take a liter of solution A, and we're going to add strong acid to it. What happens? Well, now our system has base present to react with the strong acid. The strong acid reacts with the base. Hang on. Okay. Erase this. Get a better start here. The hydroxide is going to react with the acid part of my system. So HCN reacts with the, the cyanide ion is going to react with the strong acid, H+, to form HCN. So some of my base is going to get converted to the conjugate acid. How do we work that out? Well, we just set up a little table, just similar to an ice table. I started out with 0.200 moles of CN. Again, a 0.2 molar solution in a 1 liter, that's 0.200 moles of the base. I have a corresponding 0.200 moles of the acid. I've added 0.100 moles of strong acid. The reaction that's going to happen is I'm going to lose 0.100 moles of my base as it reacts with the acid. The H+ concentration is going to be essentially 0. And this is going to decrease by 0.100. Let me be consistent here. Okay, and the HCN is going to increase by 0.100 molar. Okay, reaction goes all the way to the right-hand side. This reaction has a large equilibrium constant. The K for this reaction equals 1 over the Ka. All right, so if you need to prove to yourself that this reaction essentially goes all the way to the right-hand side, you can prove that by calculating that K value. It's going to be huge, on the order of 10 to the 11th. All right, at equilibrium, therefore, I am going to have less of my cyanide, 1/10 of a mole of the cyanide, essentially 0 of the H+, okay, at least from the strong acid perspective, and I'm going to increase my amount of the HCN. Okay. Take these into my buffer equation. pH again is equal to the pKa plus the log of the concentration of the cyanide divided by the concentration of the HCN. I know it gets old, but this is how you get good at this stuff. Plug it in. pH is going to equal 9.21 plus the log of the base concentration, which is going to be 0.100 molar, divided by the acid concentration, which is 0.300 molar. Okay. Notice now we do not have a ratio that's equal to 1. The ratio is actually equal to 1/3. I have more acid present than the base. The log of that ratio less than 1 is going to be negative. The pH is going to be on the acidic side, the pKa. And when I do that calculation, the pH works out to be 8.73. The thing to notice here, however, is the relatively small change in pH. The pH goes from the original, or from the final 8.73 minus 9.21. The delta pH is only 0.48 minus 0.48. A much smaller change than we saw in the previous cases. Okay, why? Because we've got a buffer. Solution A is a buffer. Solution A is a solution that resists changes in pH. That does not mean that it keeps the pH constant, but when we compare the changes in pH here relative to the changes in pH that we saw in question number 1 and question number 2, I hope you see how a buffer is able to keep that pH under much greater control. All right, let's look at the opposite situation in letter C. Get a little more space here. What's happening in C? Again, we're starting with solution from part A, our best buffer. We're adding 1/10 of a mole of sodium hydroxide strong base. Our buffer from solution A has cyanide, hydrocyanic acid present that can react with the added hydroxide, converting the acid into the conjugate base and producing some water. Again, set up a table just like we did above. Now the situation is I have a 0.200 moles of my HCN. I'm adding 0.100 moles of the OH minus. I've got 0.200 moles of the cyanide. My change is going to be minus 0.100 moles of the HCN is going to disappear. The hydroxide is essentially going to all react. The cyanide is going to increase by 0.00 moles. Okay. At equilibrium, therefore, I'm going to have reduced the amount of the HCN. Hydroxide is going to be essentially 0. The CN concentration is going to be 0.100. Excuse me. It's going to be increasing. It's going to be 0.300 molar. Again, plug into my equation. pH equals 9.21. The pKa for HCN plus the log of the ratio of the base, make that CN minus, to the acid. Again, plug that in. Notice that the ratio is just flipped. I now have more of the base, 0.300. I have less of the acid, 0.100. The ratio is now 3 to 1. The log of 3 is 0.48. The pH of my solution now increases to 9.69. And my delta pH is a plus 0.48. I hope you enjoy the symmetry here. When I added 1/10 of a mole of H+, the pH dropped by 0.48 pH units. When I added 0.1 mole of the base, the pH increased by 0.48. Okay, I hope that gives you some sense of that, of the fact that what controls the behavior of a buffer is this ratio, and because that ratio is embedded in the logarithm, changes of that ratio do not create large changes to the pH. All right? So what we've proven here is that a buffer is very effective at keeping the pH relatively constant. A change of 1/2 unit of pH is much, much different than what we saw in question number 1 and question number 2. Okay? So hope that makes some sense. Again, if not, you know who to talk to. So, buffers. Acid, conjugate base, ideally present in the same concentrations, but if not, the system still maintains some buffering capacity. All right,